Hi. What we're going to learn today is the mechanics of it are not really that bad, but there's a subtlety to it that really makes you understand what you're doing, that I'm hoping that you listen closely so that you can understand this. We're going to start up here with a fairly easy function, y equals x squared. What is dy dx? What's the derivative of y with respect to x? And I think you would hopefully agree that it's 2x. Okay? What if we said f of x is equal to x squared? And I said, what's f prime of x? What's the derivative of f with respect to x? And I think you would agree that it's 2x, just a different way of saying what the derivative is. And here's even another way. What is this saying? What's the derivative with respect to x of x squared? And you again write 2x. Three different ways of asking the same question. Now, this is where it gets a little bit tricky. What if I asked you this? What is the derivative of x squared? And there's probably a number of people who would say 2x. And here I'm going to have to say, well, maybe. Don't worry, calculus isn't broken. It's just, there's a subtlety. There's something different about this one that the other three explain more than this way of asking it. So let's just really quickly review what it means. What does dy dx mean if you have the function y equals x squared? Well, that 2x means it's the rate of change of y with respect to x. So that if x changes by 1, y is going to change by 2 times x. So if x happened to be 3, say you were at the point 3, 9, if x changed by 1 to 4, this derivative is telling you that 2 times 3 is 6, so the y value should change by 6. Now, let's see if that really happens. If you're at the point 3, 9 on this parabola, if x increases by 1, it goes up to 4, 16. It actually goes up by 7, not by 6. Well, let's see if this makes sense. The person who was sitting right here on the parabola at 3, 9 that couldn't see into the future would be seeing that slope as being 6. So they would think that it was only going to go up to 4, 15 along this tangent line. Now, because the curve actually changes its slope and increases its slope, it actually goes up by 7. So it goes up from 3, 9 to 4, 16. But what if you just went up a little bit? If you went up to 3.01, if you square 3.01, you get 9.60. Let's see, 9.0601. So that means the x value went up by 1/100th, and the y value went up by 6/100ths plus 1/10,000th. So almost exactly that ratio of 1 to 6. The key is the derivatives are instantaneous. So right here, it thinks the y value is going up by 6, and it actually goes up by more because it's changing. Okay, so let's come back to this. When I said, what is the derivative of x squared, why is that different than these other three? Because it doesn't say with respect to. When you say dy dx, by definition, that means the rate of change of y with respect to x. When you say f prime of x, it means the rate of change of f, which very well could be y, with respect to x. this says, what's the derivative with respect to x of x squared? This one, I didn't say with respect to. So if I had said with respect to x, then the answer, again, would have been 2x. But what if I said y is equal to x squared? What is the derivative of x squared if I asked you with respect to y? Well, what is the rate of change of x squared with respect to x squared? Because y is x squared. It would just be 1. So I'm hoping you see that there is a difference that with respect to is really important. And that's why it's nice to have these symbols that tell you with respect to what. So you have to be careful about just asking what is the derivative. Okay, we're doing this for a reason. Because now I'm going to ask you, what's the derivative of y squared? And now you're going to say, I hope, with respect to what? So if I said with respect to y, that wouldn't be any different than asking what's the derivative of x squared with respect to x. It's going to just turn out to be 2y. But if I said what's the derivative of y squared with respect to z, and say there was no relationship at all between z and y squared, then how much would y squared change as z changed by 1? It wouldn't change at all. So the derivative would actually be 0. So again, it's really important with respect to what? Okay, so I'm now going to ask you one more time, what is the derivative of y squared? And I'm going to say with respect to x. Now, you should then ask me one more thing. Is there a relationship between y and x? So there really is a non-zero derivative. And I'd say, yes, there is a relationship between y and x. And I could tell you what it was. I could say y is x cubed plus 2x. That's the relationship between y and x. So what that really means is that y squared is really x cubed plus 2x squared. And now, do we know how to take the derivative of this with respect to x? And we do. We have to use what? We have to use the chain rule, which we learned the last time. This is not x squared, it's a function of x squared. So the derivative would be 2, I'll put it over here, 2 times x cubed plus 2x to the first power times the derivative of this, which is 3x squared plus 2. So we can take the derivative of y squared with respect to x if I know the relationship between y and x. Let's try it one more time. What's the derivative of y squared with respect to x? But this time, I'm going to give you a different relationship. I'm going to say that y equals the sine of x. So that really means that y squared is really the sine of x squared. And do we know how to take the derivative of the sine of x squared? Yes, it's 2 times the sine of x to the first power times the derivative of the sine, which is the cosine of x. Again, we're using the chain rule. So for the last and third time, I'm going to say, what's the derivative of y squared with respect to x? I'm going to tell you there is a relationship between y and x, but I'm not going to tell you what the relationship is. So what are we going to do? Well, we're going to think of what we have is y squared. And this y is some function of x. It could be like this or it could be like this, but we don't know what it is. So how would we take the derivative? Well, we would still have to use the chain rule. We'd have like two functions. The function something squared, and then we'd have this other function of x in here that we don't know what it is. We'd have to do it the same way. We'd say 2 times whatever that other function is times the derivative of that other function. Well, since we don't know what it is, what can we call it? The only thing we can call it is y. Because y is that function of x. And then what is this over here? That's just the derivative of y with respect to x. So always, if I ask you, what's the derivative of y squared with respect to x, you can just reply, it's 2y times the derivative of y with respect to x, which you could write like this, but often, just for ease, we write it as y prime. So the derivative of y squared with respect to x is 2y, y prime. Now that doesn't just work with the function y squared. What if the function was the sine of y? Well, not the function, but what if what you were trying to take the derivative of was the sine of y, but if I was taking it with respect to y, you'd say, oh, it's the cosine of y. But what's the derivative of the sine of y with respect to x? Well, again, you'd have to think of that sine of y is really the sine of some function of x, and we don't know what that is. But we still have to do the chain rule because it's not just a single variable. So we'd have to say the derivative is the cosine of y times the derivative of that. Again, we're doing the chain rule. So the derivative of the sine of y is the cosine of y times y prime. And that will work for any type of function of y. So I want you to keep in mind that whenever we do this, we're using the chain rule. Now, why would we even ever want to do this? We're going to want to do this because we're not going to be able to take derivatives like we did before in all cases. The way we've always done it, we've always gotten y as a function of x, or s as a function of t. We were always able to solve for one variable in terms of the other, and then we could use all our formulas. This is called explicit differentiation. Hope I get this right. So, it's explicit differentiation. Now, this new way we're going to do it is we're never going to really solve for one variable in terms of the other. We're going to do implicit differentiation. We're going to have a function that isn't defined all in terms of one variable. So, we'll go over to this new board and we're going to do implicit. I'll write it here. Implicit differentiation. We're going to take this relationship between x and y, and I picked one in particular that you might recognize. X squared plus y squared equals 4. That should be a circle with a radius 2 centered at the origin. So we've got a circle, something like that. And say you wanted to know the slope of the curve when x equals 1. Well, first of all, we see this is not a function. For every x value, almost every x value, there's 2 y values. So it's actually 2 separate functions of x. So we're going to actually have two different answers, that slope and that slope, because there's two different values of y for that x. And we even can figure out what those points are. 1 comma the square root of 3 and 1 comma negative the square root of 3. We can just plug in 1 into that formula to find out what the x values are. So, before I do this implicit differentiation, which means take this relationship that's defined implicitly, first of all, I'm going to do it the old way. This one we can do explicitly. We can solve for y in terms of x. So what would y be? If you bring the x squared to the other side, you get plus or minus the square root of 4 minus x squared. We were able to solve for y explicitly. Now we did get two separate functions. The plus would be the top part of the semicircle, and the bottom would be the bottom part of the semicircle. So we're going to actually have to do this in two parts, two separate functions, but they're very similar. So this is plus or minus 4 minus x squared to the 1/2 power. So what is dy dx, or y prime of x? Because we really want to get the slope. In the xy coordinate system, the slope is always dy dx, the rate of change of y with respect to x. So we'll first just do the plus part. So using the chain rule, this is not x to the 1/2. It's a function of x to the 1/2, so we have to use the chain rule. So it would be 1/2 times 4 minus x squared to the negative 1/2, and then times the derivative of that, which is minus 2x. So altogether you get minus x over the square root of 4 minus x squared. So now if we wanted to plug in x equals 1, we get what? Minus 1 over the square root of 4 minus 1. So we would see that we have a negative slope at this point. If we were to then solve for the minus side, the only difference is minus times a minus would be plus, and you'd find the slope here would be plus 1 over the square root of 3. Now, that's something that we could have done before I even started talking today. But let's try to do it this new way. Instead of solving for y, let's just start taking derivatives with respect to x on the original relationship. So the derivative of x squared with respect to x is 2x. But what's the derivative of y squared with respect to x? We went through that over here. The answer would be 2y y prime. And the derivative of a constant is 0. So now we can solve for y prime. We could first divide through by 2, and then just get that y prime is minus x over y. So then what would be the slope at this point? 1 square root of 3. Y prime at the point 1 the square root of 3 would just be minus 1 over the square root of 3. And we don't even need to do another derivative, because we know that there's two different values of y. So we could also say, it's good, well, I don't even need another one. It could also be negative 1 over minus the square root of 3, or 1 over the square root of 3. That would get the other slope down there. So we can do it both ways. I think you might feel that this way was a little bit easier. But those of you who are not convinced of that, I'm going to give you a different relationship. Find the slope of this curve when x equals 1. I don't think we can do this explicitly. No matter how hard I try, I cannot solve that for y in terms of x. So I'm just going to try it implicitly. I'm going to just start taking derivatives with respect to x because I'm trying to find dy dx. So what's the derivative of x cubed? 3x squared minus, now I have to take the derivative of xy. Well, that's going to require the product rule because it's two things multiplied together and they're not constants. And I'm going to put a parenthesis here so I make sure the minus sign goes across this whole derivative. So x times the derivative of y. Well, what do we call the derivative of y with respect to x? It's dy dx, or y prime, plus y times the derivative of x, which is just 1. So I've done the product rule. And what's the derivative of y cubed? Remember, y cubed is just some function of x cubed. So we've got to do the chain rule. So it would be what? 3y squared times the derivative of that, or y prime. And the derivative of 1 is 0. So now it becomes a bit of an algebra game. We're trying to find the slope of the curve. We're trying to find dy dx, or in this case, y prime. So algebraically, we have to isolate all the y primes together. So if I distribute that minus sign, and then collect these two y prime terms together, so I'll have y prime times minus x, and then plus 3y squared. And then on the other, take everything else to the other side. So I can take that y minus y to the other side and it becomes y, and I can take the 3x squared to the other side and get minus 3x squared. So the last thing I have to do now to solve for y prime is just divide by this factor. So y prime is y minus 3x squared, all divided by minus x plus 3y squared. And I've got a formula that I can use if I know the x and y, plug it in to get the slope on that curve. Well, one slight disadvantage of doing it implicitly is you don't need just x. This is when x equals 1. We need both x and y. So we have to come back to the original relationship and put 1 in for x and see what y is. So if we put 1 in for x, let me do this in a different color, we get, in the original equation, we get 1 minus y plus y cubed equals 1. And taking that 1 off of both sides, I get y cubed minus y equals 0, or y times y minus 1 times y plus 1 equals 0. So there's not just one solution, there's three solutions. You have the point x is always 1, but we have three different y's, 0, 1, and negative 1. So on the graph, there's actually going to be, that relationship is going to give us three separate points on the curve. And then to find the slope, all I have to do is then plug these points into here. So when x is 1 and y is 0, you get minus 3 over minus 1. So you'd have a slope of 3. I hope I did that right. Y is equal to 0, so that would wipe right out. So you just get a slope of 3. So at the point 1, 0, you have a slope of 3, something like that. At the point 1, 1, the slope would be 1 minus 3 over negative 1 plus 3. Or negative 1 over, or negative 2 over 2 is negative 1. So at the point 1, 1, the slope would be a negative 1. And lastly, at the point 1, negative 1, if you plug in negative 1 minus 3, and in the bottom you get minus 1 plus 3. So you get negative 4 over 2, or a negative 2 slope. So without putting this on a graphing utility, I'm not sure exactly what the curve looks like, but it could do something like that. It's certainly not a function. So anyway, we took a really complicated relationship between x and y, and we were able to find the slopes of the curve everywhere. And I think you can see that the only way to do this is implicit differentiation. So that's a pretty tough thing to get in your head. Watch the video over again if you think you really want to make this solid in your head. But I'm going to give a small video after this that's just going to give you 2 more examples of implicit differentiation. So thank you.